Hello, this is Akash here. So I'm a student at Department of Electronics Engineering, Kwangwon University, a student of PhD, and with the student ID of 2023120206. I'm the PhD student under Professor Jeong Park, and today I'm going to talk about the summary of second chapter in the book Introduction to MMIC Technology. So the second chapter refers to indium gallium phosphide and gallium arsenide HBT foundries, and this is the chapter 2 summary. The instructor of the course is Professor Nam Young Kim. So moving forwards, let's talk about the learning objectives. So there are multiple learning objectives of this chapter. So uh, where understands the role of semiconductor manufacturing technology is in enabling the success mobile communication is one of them. Explore the key high performance components produced through semiconductor manufacturing processes, analyze the impact of large volume production and high yield of reducing units cost in mobile communication, evaluate the technologies choices available to RF circuit designers, including bipolar and field effect devices processes, examine the basic processing sequence involved in the fabricating BZT integrated circuits, gain insight into utilizing foundry services for semiconductor manufacturing and the importance of active and passive device fabrications. Moving forward, we have introduction foundry services, so where you can see the whole uh, foundry service is represented in the figure, and there are multiple processes which includes MPW, which refers to multi-project wafer application, which shares wafer resources facilitating cost-effective fabrication. NDA refers to the non-disclosure agreement, which is required to ensure confidentiality of the sensitive information, whereas RSR refers to regular shuttle run, which is confirmed ensuring the alignment with the project timeline. Design kit acquisition, so the customer receives the design kit from the foundry company such as Korea company including to facilitate circuit design. Marks fabrication, which is very important. After the passing the design rule check, which is DRC, marks are fabricated for the desired circuit design. And last, the process control monitoring, that is PCM, is employed to the monitor the fabrication process, providing the insight into any deviations and ensuring quality control. Next is introduction is continued for the indium gallium arsenide SBT processes. So there are like 5 different steps where we talk about the SBT process, which refers to the heterojunction bipolar transistor process, which is divided into 2 main aspects: transistor fabrication and MMIC, that is monolithic microwave integrated circuit assembly, including the backside of the chip. Another is transistor aspects. One of the part of HBT process focuses on the fabrication of transistors, which are crucial components of MMIC. Here is MMIC assembly. The other part encompasses the fabrication of the inter-MMIC, including components beyond the transistor, such as passive elements and the interconnects. Fabrication processes. The progression of the 6-inch indium gallium phosphide HBT process is illustrated in figure, and providing the visual representation of the key steps involved. And the last is dual side fabrication. Chips fabricated involves processing both the front and the back side of the wafer, with the front side typically being fabricated first and followed by the treatment of the back side. So whole process is given in the figure. So moving forward, we have again introduction continued, and here we talk about type and their material. So different types and their materials. So there are 3 different types, processes and their materials. So like high power process, that is HP processes, and the practical application. So 3 types of processes are detailed. So in the table which you can see, so high power process, high linearity process, and high speed process. So here the practical applications are PA, GSM, DSCs, and base stations, whereas with different characteristics like which have BVCO is 20 to 23 volt, FT is greater than 34 gigahertz of frequency, and DC gain is equal to or almost near to 87. Similarly, PA of WCDMA LAN, and so these are the basic informations of different types of processes. Now let's talk about the active devices. So we also said that there are active and passive devices, so we now talk about the active devices. So the active devices like SBTs necessitate amplification, nonlinearity, and a DC bias for operation, whereas 3.5 SBTs exploits the heterostructure design, capitalizing on superior transport properties like high electron mobility and velocity. So these devices are typically built on a gallium arsenide substrate with high resistivity. So 3.5 SBTs features in heterostructure junction with a band gap difference between the emitter and base, leading to improved emitter injections efficiency and current gain. Epitaxial growth enables achieving very high base doping concentration and thin film base thickness, thereby enhancing the electromobility in 3.5 SBTs, where the figure representation is given in the figure. So in the active devices, we also have indium gallium phosphide and gallium arsenide SBT devices. So there are different images are represented, which talks about micrograph of the particular SBT, the SBT EP structure, and the lays between emitter and the base. So here we have the different processes are like HL processes of active devices based on the indium gallium phosphide SBT, known as for its instinct linearity due to uniform current gain characteristics. Then we have indium gallium phosphide and gallium arsenide SBT MMIC design considers self-heating effect due to gallium arsenide's lower thermal conductivity. Then thermal resistance is one of the device characteristics, which is crucial for determining the junction temperature and SBT lifetime, with Korea company including processes offering low earth for improved lifespan. Now gain characteristics influenced by collector current, independent collector capacitance, and high early voltage impacting the key electrical characteristics. Now the VVIC model used to account for self-heating effect, adjusting parameters like current gain and base emitter voltage based on junction temperature. Indium gallium phosphide layers in 3.5 SBTs reduces surfaces recombination current, lowering one of noises and improving oscillator phase noises performance. Now we have active devices modeling. So which here the picture shows the different modeling aspects. So parameters for the VVIC model are extracted into the section requiring parasitic in strings, DC, AC parameters, and accurate model. DC measurements conduct using a DC source monitor, that is SP4142B, while AC measurements are performed with a vector network analyzer. Modeling software like integrated circuit characterization and analysis program IC-CAP and advanced design system as utilized for the parameter extraction and optimization. IC-CAP facilitates instrument control, data acquisition, graphical analysis, simulation optimization, and statistical analysis, and can be linked to external simulator like ADS. Now, based on 6 inches indium gallium phosphide and gallium arsenide SBT devices technology, with one emitter finger having a wide width of 3 micrometer and an emitter length of 20 micrometer, achieving specific DC current gain, breakdown voltage, and high frequency performance. Moving again, so we have completed active devices. Now moving to passive devices. So the introduction of passive devices. So the MMIC design extensively employs passive devices for various functions like impedance matching, DC biasing, phase shifting, and filtering. Key passive devices in MMIC design includes distributed transmission lines, MIM capacitor, spiral inductors, resistor, via holes, and pairs. These passive devices play a crucial role in achieving desired performance, characteristics, and functionality of MMICs. The section outlines the importance and uses of passive device type in MMIC design. Understanding these passive devices is essential for the effective MMIC layout. Now we have transmission line in the passive device. So here you can see that a transmission line is represented with the figure, and we have microstrips where microstrips is there, which is a flat strip of conductive material separated from ground plane by dielectric substrates such as gallium arsenide. Unlike strip, line microstrips lacks a second ground plane, leading to higher radiation loss, thus making it inaccessible for circuit trimming. It requires consideration of an effective dielectric constant due to the field distribution across the dielectric and air. Design curves aid in selecting microstrips dimensions for achieving specific characteristics, impedance, or other desired parameters, making it useful for microwave circuit interconnections. Now again, in the passive devices we have MIM capacitor. So MIM capacitor, the reference plane of MIM capacitor devices is given in the figure representation, which can be visible, and this represents the overlay and interdigital capacitor used in MMICs, with interdigital capacitor limited to value up to 1 picofarad due to size constraint. So MIM, that is metal insulator metal capacitor, are favored for their high capacitance per unit area, enabling smaller and cost-effective circuits. They consist of two metal plates separated by dielectric layer, with the dielectric overlapping the first metal layer. Capacitance values typically range from 0.4 to 30 picofarad, are determined by the area of the air bridge post. Metal insulator, metal capacitor, minimizing parasitic capacitance with features like air bridge, but pinholes in the dielectric layers can lead into chip failure. In the similar way, the passive devices also talks about the spiral conductors. So spiral conductors, a reference plane of spiral conductor is given in the figure, which is taken from the Korea component includings. So here is spiral conductor known for their high Q factor, widely used and offered by the Korea company, with inductance value ranging from 0.28 to 24 nanohertz. So Korea company provides two types of square inductors, that is EA type with an entire air bridge structure, and PA type formed from the micro strip line. In EA type, the air bridge post size is typically 1 micrometer, smaller than the air bridge microstrips line width, maintaining a consistent gap. The inner diameter of spiral inductor is defined as the minimum spacing between the majority of the inner metal interconnections. Spiral inductors are specified by the number of turns microstrips line with inner diameters, with the turn spacing fixed at 5 micrometer for the stability across all patterns. So in the same way, we also have resistor in the passive devices. Resistor as considered as the passive devices. So resistor, one of the resistor configuration is given in the figure. So in the MMIC resistors utilize a doped semiconductor layer or deposited thin film resistor layer, often composed of nickel chromide, and the spluttered thin film resistor offered superior linearity and lower temperature coefficient compared to the alternatives. They can achieve seat resistance up to 50 ohm per square, providing convenience for circuit designers. Detailed layout rules for NICR resistors are outlined in the subsequent section on the layout design structure. So moving forward, we also have via hole as an passive devices. So via hole, the via hole configuration is given in the figure, which you can see. So backside via holes connect from the side devices or RF circuits to the metallized back inside for grounding and thermal dissipation. They are molded in RF devices as a single port from the front via pad to the back inside ground. Layout design rule. So this is another subtitle, which is layout design rule, and there are many subtitles. So one of the thing is general consideration. So the stepping rule is like, so maximum stepping tile size on the wafer is restricted to 15 mm width and height, resulting in chips shapes being perfect squares. So transistor orientation is standardized to ensure consistency, typically indicated by the groove at the bottom of the wafer. Now we have multi-project wafer. Processes allow multiple users to share a wafer to reduce cost, with each user designing their desired circuit based on given rules. Now, layout database submissions should be in GDSIIF file format with default units utilizing standard cells libraries supplied by K company. Design rules includes using acute angle corners 45 or 90 degree and avoiding donut pattern on metal layers. Similarly, we have design rule type. So there are 6 types of simple layout design rules described in the table, and the figure is also there. Layer 1, layer 2, and the 6 different design layout is given: width and length, spacing of layer 1 or 2, extension of layer 1 to 2 to 1, overlapping of the layer 1 and layer 2, surrounding of layer 1 by layer 2. So this terms is width, length, spacing, extension, overlapping, and surrounding, where the definitions are being presented. Moving forward, we have layer description. So we have 19 layer, and 19 layers are given. So K company utilizes 19 layers in their fabrication process, detailed in the table. Each layer serves a specific purpose and is crucial for the component fabrication, while some layers are provided by the company and should others require the design by the customers, functions like register and transmission lines. So here there are 19 like emitters isolation, first base potentials, base contact, second base pedestal collector contact, isolation mesh each, nickel chromine resistor, first nitride via, interconnected metal speed, interconnected metal, second nitride via, air bridge post, air bridge metal, final passivation layer, backside via, and backside script strip. In the same way, we also have concrete layout design rule, which is given here. So this is a particular design rule for the nickel chromium, where you can see there is IE and CR and IMS, and this is the particular layout represented in the figure. Then we have DRC, design rule check. So design rule check, we have to define or select the design rule, then run the design using the defined or the selected rule, load the result, and view any errors that were found. So this is a particular schematic or the flow of the DRC. So DRC stands for design rule check, ensuring design meets. That 2 types of DRC exist, one focusing on minimum width and spacing. So produce starts defining the selecting design rules and from a table, and circuit run based on these rules, and errors are identified in the DRC message window. This process helps in engineers to locate the locate and rectify any errors in the design. Thank you very much. This is the overall summary of the second chapter of MMIC technology. Thank you. This is Akash Dev again.